Okay, dude, this is a brief little video that I'm making on modeling with mathematics, in which I'm just going to provide us with a worked through example here. We'll work through our own, but the idea is to understand that often we collect data in real world application situations, and what we hope to do is basically describe that data using some sort of model. It could be a linear model, a quadratic model, absolute value model, exponential, you name it. But we use models to help us make predictions about what might happen based upon data that we have observed. So such models, like I mentioned here, allow us to make predictions. We're going to look at a situation here where we have some time and some height at a given time, okay, in feet. And basically what you're seeing here, it says the table shows the height y, or the output y, of a dirt bike x seconds after jumping off of a ramp. So it says what type of function can you use to model the data and estimate the height after about 1.75 seconds. So here's our idea. We want to make an estimate at about this time. How high off the ground would that be? At 1.75 seconds, how high off the ground would it be? So observing our data here, we have this time in seconds, and you'll notice it goes from 0 to 2 seconds. Now on our graph over here, these points have already been placed on the graph for us, these data points, but we have 0 seconds, we have 8 feet off the ground, and you'll notice that we're using increments of 5 on our y-axis here. So 8 would be just below 10 here. The plotted at a half a second, 20 feet off the ground. 1 second 24, and then we notice that it proceeds back through 20 and then 8 again, and of course we have something that looks like this. Well, to understand this problem, we say we need to identify the type of model that we can use here, what type of function we can use to model this. And it seems pretty obvious to me that we would use a quadratic model. Okay, so this is a quadratic model. It looks like our quadratic parent function. Of course, those tend to open upward like this, but we look at this as being some transformation of that, where it's maybe reflected over and translated over and up. Okay, so our plan here is to create a scatter plot of this data. After we've done this and fit a model to it, though, we have a curve that resembles this right here. Now I don't have an equation for this curve, but we can say that at about 1.75 seconds, you notice this has already been drawn upon, but if this is 1.5 right here, we have 2, then 1.75 is the midpoint of those two, and all we really need to do is trace it up and over here, okay? And what they've come to a conclusion at, is what we've come to a conclusion to, or can draw a conclusion about, is essentially that it'd be about 15 feet off the ground according to our model. Here's what I'd like to do though. Using the same kind of graphical approach here, understand the problem, make a scatter plot, and then kind of fit a model to it. Let's take a look at what we have here. It says this table shows the amount of fuel in, say, a device or a chainsaw, in this case, over time. It says what type of function could we use to model the data, and when will a tank be empty? So we notice that our time x down here, this is x, and this is time. Okay, this is in minutes. And we know that this is the amount of fuel remaining. So we have fuel remaining. So our y-axis here, and we're measuring this in fluid ounces. So I have fluid OZ. Okay. So in terms of what data values we're seeing here, we're seeing at time 0 minutes we had 15 fluid ounces, and it looks like our time is going by in increments of 10-minute intervals here. And I noticed that as 10 minutes goes by, continues to go by, the pattern here is that we're losing 3 ounces of fluid about every 10 minutes. This is a pretty solid rate here. So let's go ahead and start by maybe labeling our x and y axes here. But I'm going to go ahead and say, well, then this will be okay for my 10 right here. 10 minutes, we'll put on these major lines, 20, 30, 40. And you know what, we don't have 50 on here, but I do want to place this out here. And when we look at the fluid ounces, it looks like it's going by increments of 3. So perhaps I'll do this. I'll say that every other is 3. So we have 3, 6, 9, 12, 15. So as far as graphing this data is concerned, we've got our understanding of the problem. Let's make our scatter plot, which is just a graphing of this data. So it looks like we have an input-output pair of 0 minutes, 15 fluid ounces. So that would be this point right here. And we say, well, 10 comma 12. Okay, so at 10 minutes we have 12 ounces left. So 10 minutes we're going to trace this up and put this on at 12. At 20 minutes, looks like we have 9 fluid ounces left. At 30 minutes, it looks like we have 6 fluid ounces left. And obviously, we can see what kind of a pattern is kind of popping up here. But the really big question is this: what kind of a model could we say would approximate the relationship we're seeing between time and the number of fluid ounces that are in this chainsaw? And I would say that this would be a linear model. And using this linear model, the question becomes this: when is the tank going to be empty? Now, interpreting this graphically, we say, well, the tank is empty when it reaches 0. So basically we're saying is, when would this model intersect the x-axis? And we could really just predict it's probably going to do so at about 50 minutes. So we say at approximately 15 minutes. Okay?